this as usual. Hello and welcome back to Calculus 2. We are starting these advanced integration techniques. Well, quotation marks around advanced. It's advanced for undergraduate, but far more advanced stuff later. So we're going to discuss a number of different techniques. So we are starting with integration by parts. That's the first technique that we are learning. And this technique is going to be the backwards product rule. So you know that integrals and derivatives are opposites of each other. So those operators are opposites of each other. You also know by now, you should know, that the U substitution is backwards chain rule. And now with this one, you are learning backwards product rule. There is no backwards quotient rule. I'm just going to put that now on the table. So integration by parts. I'm going to derive this formula from product rule. And then we're going to also see visual proof, the graphical proof for it as well. So we're going to start by saying that the derivative of uv is u dv dx plus v du dx. So we know that the derivative of the product is copy the first derivative of the second plus copy the second times derivative of the first function. And what I'm going to do is I'm going to integrate each one of these and see what I get at the end. So if I integrate in terms of dx each one of these, observe that these dx's die and the derivative cancels the integral on the left, and I am left with uv is equal to integral u dv plus integral of v du. So at this point I'm going to solve for integral of u dv, and that will give me uv minus integral of v du. Please note at all times that these u and v are functions of x. So u is u of x, it's a function, and v is the v of x, which is also a function. We are done. This is it. This is your formula. Actually, this needs to be far more dramatic. There we go. So this is our formula for integration by parts. So another way to understand this is to just take a look at a function like this. So you have area 1 and area 2. Also note that overall area is area 1 plus area 2. So if you observe, you can calculate the area of A1 by looking at the representative rectangle du. So area A1 is going to be integral of function v du, because du is the variable there. And A2, if you look at the horizontal, which will be dv in this case, is integral of u dv. Now you can also see that the entire area A, which is a rectangle, is uv. And when you plug these three into the formula up there, you get this expression here, which simplifies into the expression below. So you have a graphical approach, and you have direct derivation from product rule, whatever makes more sense. Again, this will not be a question on the exam because it's not honors section of the Calc 2 class, but some of you might want to know where these formulas come from. So none of the formulas in mathematics are just, you know, given on a tablet and then you, 10 at a time, you know, and then you display them.
Psi arrow for area 2, and you better explain really well.
What happened?
What was the area, was the thing, was the area 2? Can you explain it or something?
Yeah, area 2 is the one on top. Area 2 is this area here. That's area 2. So if you look at it, right, it's this horizontal representative rectangle is dv, right? So it's u dv. That's a dv, and this is du. So this is the a2, u dv, integral of u dv. So when you plug everything in, you will get that uv is equal to the integral of v du plus integral of u dv, and you solve for integral of u dv, you get uv minus integral of v du. Again, that's the formula we are after. So practice, 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 and you will eventually be able to recognize which of these formulas, which are the proper integrals to use this method. So I'm going to show two separate problems here which look very similar. Observe that the one on the left has x squared as the exponent and the one on the right just has x, right? Now, my hope is that everyone looking at this would immediately say the one on the left is just a basic u sub, right? It should be clear as a day because you have function derivative pair, right? So the one on the left is a u sub. The one on the right is by parts. So what we are going to start building immediately from lecture 1, which is this one, is you first look at the problem and ask yourself, is this basic integration? If not, then you go and you say, is this u sub? If not, then you ask yourself, is it by parts? So you're not going to look at the problem and say, oh, it's by parts. Because you try and get the problem done by the basic techniques first. And if the basic techniques don't work, right, you're not going to use sledgehammer to put the picture on the wall, right? It's a little nail and you might smack your fingers, right, if you swing too hard. So problem on the left is u substitution. Problem on the right is by parts. Now let's see how this by parts works. So, and I'm going to do this example here. So I have, as you can see, this problem here has 3 parts. There is a part number 1, part number 2, and part number 3, because they all have multiplication in between. You could have just du to be part. You could have x to be part. You can also have x e to the x to be a part, or e to the x and du, or x du. So any combination of these, or each one individually, could be a part. So I have 3 separate parts, but I also have combination of these. So we're technically looking at, what, 6 parts? There we could possibly make. Yeah. So the way I work with these problems is I first take a look at how many parts I have, and then I realize that my u could be x, could be e to the x, could be the whole thing, right, x times e to the x. The dv part must be du, and maybe something else with it. So, and your lab 2, addresses this type of thinking on learning how to, teaches you how to pick proper stuff. If you can start lab 2 tonight or tomorrow morning to reinforce this, that'd be superb, because you will be discovering the pitfalls, and because the lab is designed in such a way, lab 2 is designed to really help with this, but you have to do every single part. It has like 30-something problems on the entire lab. It's going to be like this thick when you're done with it. It's, the lab 2 is insane. And then it goes back to few problems in lab 3 and, you know, a little bit more in lab. The lab 2 is hefty. Start tonight. So here's what I'm going to do. I'm going to say, oh, first, before I do that, I'm matching this to UDV, right? So I know that at least this much matches. But I'm going to say u is equal to x, and the dv is equal to e to the x dx. Now, the derivative of u is going to be u is dx, right? That's like u subpart. On the other side, I have to integrate here to get v, right? I have to integrate these guys. Don't put these integral signs if you're using the same color, because you'll be confused. So I have to integrate, and the integral of e to the x is, again, e to the x. We do not put plus c here because there will be a plus c for the entire problem later. So I don't need that. And I'm going to put my magic arrow here, which actually gives me the formula. So if you write it this way, u, and to the right dv, and then you go down to find du and dv and v, by putting in this arrow, you actually get the formula. Because the formula says uv, which is x e to the x, minus v du, integral of v du. Huh. You see what it transformed into? It transformed into a basic integral, which I can do, and then we put plus c. Don't forget to factor out e to the x at the end, because we like factored form. So here is the complete introductory problem that outlines the method. Now, for those of you who really want to learn this, you are going to try other combinations, and you will see that the problem will become worse and impossible with any different choice than this one. So if you are inclined to explore, you are going to put e to the x here and keep x over there and see what kind of horror you're going to get here. I promise you that this problem is going to explode in every other case unless you choose this. Now you say, well, how do I do that, in 2 weeks on a test, right? Well, A, practice, and B is when you see something not working, well, you switch it around. I mean, what's the definition of insanity? Trying the same thing over and over again, hoping that you'll, yeah, exactly, right? So when you are running, you run into a brick wall, you turn around, you run the other way, right? You're not going to go boom, boom, boom. So if one setup that you picked, which looked good, if one setup gives you this insane thing that doesn't work, obviously switch it and do something else. Now, in this case, I gave you the problem. So now I'm telling you, use the same setup and same everything, work on x times sine x in your notes. So the next problem is x times sine x. Now, unfortunately, that problem is going to look the same, except you have a little bit different calculations. So you will be picking the same stuff around. So go ahead. Practice integral of x sine x dx and just use the same same steps, same choices, same everything. Yes.
I switched the dx.
Well, it can be done because you get worse, right? Instead of getting something that you can integrate, you should get x squared over 2 times e to dx dx, and you just made it worse, right? And if you try it again, it will go into x cubed and x fourth. Yeah. So instead of losing the part that's making you not be able to do the problem, you are making that particular part worse. So that's how, and that issue grows when you need to do nested integrations by part. Do it twice, do it 3 times, do it 4 times. As long as the problem is getting simpler, you keep doing integration by parts, awesome. If the problem is getting more complicated, you are doing it wrong, shuffle things. So we'll deal with those as we move along. All right, so I'm hoping that you have your u equals x, dv equals sine x dx, and then you do the derivative integral, put it together in a formula, integrate, and you have plus c at the end. Mathematics is exactly one right answer, and if you know it.
With e to the x, did you replace it with dv, the integration?
Yeah, this is your uv minus v integral v du. Right? Okay. If you're looking at the formula. And that's, look, u v minus integral of v du. So I just plugged in what v is, just replaced in the formula. All right, let's take a look at that sign question together, and then pick some other interesting problems to work on. By the way, this is it. Now, you will sometimes have to do it twice in a row, 3 times in a row. That's all it is. So integral x sine x dx, we are going to pick u equals x, dv equal sine x dx. We differentiate u, we integrate to get v. I hope you have this negative there. And then I like to put my arrow because that gives me the formula. So it's uv, which means negative x cosine x, minus the integral of negative cosine x dx. Now this negative makes the positive in front. So that's the one I'm solving, and I get negative x cosine x. The integral of cosine is positive sine, so plus sine x plus c. So this problem is identical. You can have, x times cosine x, or whatever else that can be integrated. What happened to for whatever reason, my textbook went away. So, when I pick more of these examples, Probably tomorrow I am going to do more. Maybe I'll do part 2 of this lecture tomorrow as well, and then move to the next 2 sections. Just make sure you review trig for tomorrow. We only have 15 minutes left now, so it's gonna be good for few examples, but I would like to do more than few. All right, so let's take a look at chapter 7, 7.2. So let's pick some of these problems. Ooh. All right. So how about this? This is number 16. So you're looking at this x, ln x, and you are tempted to pick what as u? X, because that's what we did in the previous 2 problems, right? Well, in this case, you won't. Because if you pick u equals x, you are left with what? dv is ln x, right? Can you integrate ln x? No, right? You can't integrate, not yet. But even if you can, it will make the problem worse. Once you learn what the integral of ln x is, go back, revisit this problem, and you will see that if you pick u equals x and dv ln x, it's going to be bad. So for this one, you have to switch, right? So your u is ln x because you can differentiate that one, right? So let's see what you're going to get when you make a choice of u equals ln x and dv is x dx. Let's see what happens. Yes. You done? Or you stuck it out? And guys, don't forget plus C at the end. All right? So for this particular problem, if you try to use x equals u, you will see that you'll get stuck. So I'm going to write it and then erase it. So if you go what we did earlier, we differentiate the first one, so that looks good so far. But then when you need to integrate this, we don't know what the integral of ln is. And even when you learn it in about 3 minutes, you will see that if you do the ln integral there, the problem will just become insanely complicated and worse. So we're switching gears. We're trying something else because what we wanted to didn't work out. Just like in life, right? Well, it's mathematics, right? Models the life. So what's du? Du is 1 over x dx. And over here, v is x squared over 2. Again, we don't put plus c there. We'll put plus c at the end of the problem. I'm going to put the arrow there. And I'm going to say x squared over 2 ln x. That's my uv. Minus the integral of v du. Oh, this cancels, right? So these guys cancel. And I have x squared over 2 ln x minus, I kick 1/2 outside, and all I need to integrate is just x dx. So this becomes x squared over 2 ln x minus 1/2. Yeah, how did you get cubes? I've seen too many of you having cubes there. This is x squared over 2. So you were right. Ah. Yeah, okay. And now we have x squared over 2 ln x minus x squared over 4 plus c. And you can see that we can kick out x squared over 2 to give you ln x minus 1/2 plus c in the factored form. Nice. So here is the fun question. Now you can use this to troll your friends when you go out, right? Ask them what's the integral of ln x. I can guarantee they're going to go, oh, 1 over x. Nope. Let's see what it is. You have friends, right, that you go out with. All right. Check. So what is the integral of ln x? Well, let's do it. You can ask, you know what's the setup?
I don't know how to do this.
Oh, you memorized the answer. Okay. Now we're going to use integration by parts to solve this problem. What should I pick as u? What should I pick as dv? Perfect. All right, so you just solved problem for you. Now, do you see that this is a common sense choice? Because you can't pick ln x to be on a dv side because that one is to be integrated, and that's what you're trying to figure out. And also, if u is equal to 1, because everything else was in dv, the derivative of that is 0. So the whole. Okay. All right, go. Derivative, integral. Yes, got it? What's your plus? Got it?
I got 1 over x minus 1. yes, x dx.
All right, so it looks like that you guys got this. Great. So now you know what the integral is, right? We have the integral. Oh, sorry, no integral. First, we have uv, which is x ln x, minus the integral of x times 1 over x dx. But these guys cancel, so it's just 1 there. So you have x ln x minus the integral of dx, which is x ln x minus x plus c, and you can factor out x, ln x minus 1 plus c. That's what the integral of ln x is. Now, I can write it as a formula. I mean, if you want to memorize it, you can. You know how to get it. So now try to imagine going to the previous problem and picking u equals x and dv equals ln x. Because this side here gets integrated, you will be integrating ln x, which means that this part over here would be this, right? And you see how insanely complicated then it would become. So, don't do it. And if you allow me another 2 minutes over class time, I will work out a case where you have to use nested u sub, so multiple by parts. So we already discussed the situation that looked like this. This was our first example we did. But now I would like to look at x squared e to the x dx. So I want to look at this one, and it has x squared here. Now you might say, oh, u sub, because I have x squared and x, but that x is in the exponent of e. U sub doesn't work here. The square is on the wrong x. So we have to do integration by parts. But integration by parts here would not eliminate the bad x squared. It would just bring it down by 1, which means you have to do integration by parts one more time to eliminate that x completely. So this one is, as usually it goes, a little bit more algebra, but it works out at the end. So now, as you can see, you have 2x dx here, and your v is e to the x, and upon placing the arrow, we can get our first stage, which is x squared e to the x minus the integral of 2x e to the x dx. Now, you should be recognizing this problem here as the first problem we did. Yeah, there is a 2 there, but it's a constant, you can kick it out. So you see how we reduced the new problem with the square using one integration by parts. We reduced it to actually the introductory problem. So what you have to do, you have to do procedure one more time, right? So there's going to be another u equals, in this case, you can say 2x if you want to. And dv is e to the x dx. So we are doing this again. And then du is equal to 2 dx, and v is still e to the x. We have our arrow. Now, the purple only works for the integral. You still have to copy the x squared e to the x piece. Minus, And then in these brackets is the new integration by parts, which is 2x e to the x minus the integral of 2e to the x dx. So these brackets contain the second integration by part, which was done just for the integral, and we are copying the first term down. So now this is x squared e to the x minus 2x e to the x. Minus and minus gives me a plus. An integral of 2e to the x is 2e to the x plus c. We can kick out e to the x. And we are left with x squared minus 2x plus 2, everything plus c. And that's the answer. We did two integration by parts back to back to eliminate x squared. Just 1 second. How many integration by parts do I have to use if this was x to the 5 e to the x? 5 of them, right? Because for x was the first power, we did one integration by parts. For x squared, we did two integration by parts. For x to the 5, you will have to do 5 integration by parts. And this would be x to the 5, x to the 4, x to the 3, x to the 2, right? All the way down. And you will have e to the x in front again. It's very systematic. It just takes time to get used to this because you haven't done it before.
So with 2x, is it supposed to be x squared because you're doing the 1/2 x squared on that, and the 2 and then you bring it outside?
I'm not integrating up.
No, with the integrating up with the 2x e to the x.
This one, right?
Yes, isn't that supposed to be like x?
I did by parts. The 2x is here. E to the x dx is here. Yeah. You can't integrate because there's a time.
That's the time? Or?
Well, there's 2 times x times e to the x times dx, right? So I did it by parts. 2x e to the x dx is the procedure, and then turned it into this.
Because I honestly thought when we were integrating the entire time because we were
I did integrate at the end from here to here. But I can't integrate this because this is not basic integral. You can only integrate when it's a basic integral. But this one is x, so I have to use this procedure to remove the x. So the procedure spits out this extra term, and the rest that is left is easy. Now it's specific. It takes some time to
like, how come it's not like 2 to x and to e to x?
Okay. Which one?
The second one. Then.
This one?
Yeah.
Because the real integral of e to the x is just e to the x.
Yeah,
it's
but
constant copy.
So yeah, take
It's
as
a constant. You can kick the constant in front of the integral, and integral e to the x is e to the x, right?
Yeah, okay.
Perfect. We will do more problems tomorrow for this. So we'll have part 2 of the integration by parts. So see you all tomorrow, you know, the place and the time.